Hi everyone, just wanted to take a minute to talk a little bit about perpendicular bisectors and angle bisectors, the two kind of bisectors in a triangle. And this is going to lead into discussions of our points of concurrency and finding different centers. All right, so let's actually make sure that we know what we are looking for. So our goals of the day are to determine measures in triangles using different bisectors. So the angles and the perpendicular bisectors. And then we're going to describe the incenter and circumcenter of a triangle and what they actually represent. All right. So we do have two pieces of information that we care about. We have something called the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. So in terms of what the perpendicular bisector theorem says, it says if I take a perpendicular bisector of a segment. Now remember, perpendicular bisector, what does that mean? That means two things. One, it goes through the midpoint because it's bisecting, all right? So this point right here, Y, that's your midpoint, okay? And it's perpendicular, okay? So it's perpendicular. So we have a right angle there. You can even see it drawn in. So it's a right angle, also meaning that the slopes would be opposite reciprocals, as a quick reminder, okay? So if I know I have a perpendicular bisector and I take any point on that perpendicular bisector, it could be this point right there. It could be, I don't know, it could be this point down here. It could be this one way down there. Whatever, it doesn't matter. Any point on that perpendicular bisector, it is going to have this property. It's going to have the property that if I connect that point to the end points, my other segment, they will be congruent. Okay, so this is congruent to this. This would be congruent to this. I'm not saying that these ones are congruent to this one. I'm just saying that this is congruent to this one. Okay, so that's what it says. If I take any point on my perpendicular bisector and drew lines to the endpoints of the segment, it will be congruent. Okay. The converse is saying, if I have a point that is equidistant from the endpoints on the perpendicular bisector, right? So this one is saying, I know I have a perpendicular bisector, and I pick any point on it, it's equidistant from the endpoints, right? This from this is the same, right? Both sides are the same. This one, the converse, is just saying, if I have a point and it is equidistant, so this is congruent to this, that means this is a perpendicular bisector. That means that this is a right angle, and that means that this right here is a midpoint, which means that these two are congruent, okay? So when in doubt, really what you've learned here is if you don't know what to do, set it equal to each other, all right? So let's do some actual practice. So I know, my goal is to find TP. I know that LJ and JP are congruent, right? That's what those little lines indicate. That means they're the same. So this is congruent to this, and this is congruent to this. And it's also a right angle, which means this is a perpendicular bisector. So if this is 7, this must also be 7. So TP is also 7. Now, looking at this one, I'm actually given all the information already off the top of the head, right? This would be from the, by the way, this is from the perpendicular bisector theorem. On this one, what do I know? Well, I know that these two sides are congruent, right? They are equidistant from the endpoints, which means that this AV is your perpendicular bisector, which means that these two are congruent. So to solve this, I have to set them equal to each other. Don't forget, that's what those lines mean. So you really didn't need to do anything with that. All right. So subtract the 3x, so we get 4x plus 2 equals 10. 4x equals 8. X equals 2. Now, it's not asking for x, it's asking for VU. Now, VU is 3x plus 10. It doesn't matter, by the way, if you did OV or UV, because they're the same, just to keep that in mind. So then we have 3x plus 10. We know x is 2, so it would be 3 times 2 plus 10, which is ultimately going to be 16. Okay. Last one, let me move my face out of the way here. Okay. All right, so what do I know? I know that these two are congruent, and this is a right angle, so this is a perpendicular bisector. Because this is a perpendicular bisector, these two sides are congruent, right? These two distances from k to n is the same as from k to h. So again, I'm going to set them equal to each other. Again, when in doubt, if you don't know what to do, try setting them equal to each other. Okay, so I have 2x plus 10, because I subtract the x from both sides, divide by 2, x equals 5. But it's not asking for x, it's asking for kn, so kn is x plus 5. I'm sorry, x plus 10. So 5 plus 10, 15. Okay, so that is ultimately what it's looking for. Now, moving on. The point of concurrency of the perpendicular bisectors. Before we go into what that is, we need to talk about what our point of concurrency is. So point of concurrency is just where 3 or more lines meet, or segments or rays, or where 3 or more things meet, right? So if I took, this line and this line, I don't want ones that meet like this, right? They have to all meet at the same point. So not that. I would need a point where all 3 of them are meeting. So right off there. That would be a point of concurrency where all 3 of them meet. Okay. So when we're dealing with triangles, if I did the perpendicular bisector, I'm going to get something like this, and then maybe something like this, and then something like this. So if I drew all 3 perpendicular bisectors, they are going to meet at a point called the circumcenter. Okay, the circumcenter is the point of concurrency of the perpendicular bisectors. So there are 3 perpendicular bisectors in a triangle. If you took each side and drew the perpendicular bisector, they would all meet at a point. And that point is called the circumcenter. It represents a certain thing. It actually represents the center of a circle that would go through all 3 of the vertices, doing something called circumscribing the triangle. All right. So if you look at this picture here, you can kind of see what it looks like. So the circumcenter here, see, it's going through these 3 vertices. Circumcenter here, it's going through the 3 vertices. No matter where your circumcenter is located, it will go through the 3 vertices if you drew the triangle around it. Okay, the circle around it. That's exactly what it is, the circumcenter of a triangle. You also can notice here that if it's acute, it's inside the triangle. If it is obtuse, it is outside. And if it is if it is a right triangle, that would mean that your circumcenter would actually be the midpoint of the hypotenuse, the longest side. Okay, that's just kind of some extra information, but that is what the circumcenter represents. The other thing you should keep in mind here is that if I just drew a perpendicular bisector, you'll notice it's not going through the vertices. All the other ones that we care about later on will go through the vertices, but not this one. So let's actually look and kind of ask ourselves, well, why is this true? So we have something called the Circumcenter Theorem. The Circumcenter Theorem says, if I have a circumcenter, which again is the point of concurrency of the perpendicular bisectors. Perpendicular bisectors have 2 pieces of information about them. They are right, they are perpendicular, which means they form at a right angle, and they go through a midpoint. So I mean, this is congruent to this, that part's congruent to that part's congruent to that point. It also means that these are congruent, okay? And if I were to draw this, that's a shared side. So the reason why this theorem is going to be true comes down to side angle side, okay? Right, so those triangles are congruent. But anyway, so what it says is if I have a circumcenter, it is equidistant from the vertices of the triangle. Okay, so if I drew lines from the circumcenter to the vertices, they would be the same. This is 5.2, this is 5.2, this is 5.2. They are not inherently on the perpendicular bisector. I cannot stress that enough. See these gray dashed lines? Those are the perpendicular bisectors. Okay? The circumcenter, the line from, or the segment from the circumcenter to the vertex is not necessarily on the perpendicular bisector, but it is the same distance away from every single vertex. That doesn't mean, that also applies to the ones even when they're outside the triangle, okay? So let's practice with that. So point P is the circumcenter, which again means that we have perpendicular bisectors. List any segments congruent to each given segment. So Bn. So Bn here, I need to figure out which segments, or multiple segments, it is congruent to. Again, this right here, where the right angles are, this is a perpendicular bisector. Perpendicular bisectors are perpendicular, so you get the right angle, and they go through the midpoint. So it's going, this is the midpoint. N is a midpoint. So that means Bn and Nt are going to be the same. Okay? Now, that's all we know thus far, right? If we went back to that previous picture, if I gave you this one down here, this one's congruent to this, but that's it. Okay? Same thing with that one. Now, BL, that's a little different. BL goes from the circumcenter. Okay. Every time. Sorry, I apparently forgot to change these. Ignore that. BKT. All right, so P is the circumcenter of triangle BKT, and BL is the segment from the circumcenter to the vertex. Okay, so L, this is from the vertex to the circumcenter. What do we know when we look at vertex to circumcenter? Vertex to circumcenter is 5.2. Vertex to circumcenter, 5.2. Vertex to circumcenter, 5.2. So we are looking for the other ones where they are vertex to circumcenter. So that'd be TL and KL as well. Okay. I forgot that the place I got this from had a mistake, and I even did this with my other class and totally forgot about it. Anyway, that's everything about circumcenters. Okay. So let's move on to the next bisector, the angle bisector. Now this is very similar to what we just looked at. So we have the angle bisector theorem, which just says if I have a point on an angle bisector, now the angle bisector, mind you, just cuts the angle in half. So this part's congruent to this part. If I pick any point on that angle bisector, it could be this point, it could be this point, doesn't matter. And I drew a line to the opposite sides of the angle that are perpendicular, right? I have to pick the perpendicular lines. Then these are going to be congruent. Okay, this is congruent to this. This wouldn't be congruent to this one, okay? Similarly, if I knew I had a point that was equidistant from both sides of an angle, right? Both of the rays of an angle, it would be on the perpendicular bisector. So if I know this, I know this. Okay? If I know this, I know these two sides. Okay. So it's very similar to the last one. So sometimes it's very easy to mix them up. All right. So here, what do we know? We know that M is equidistant from YW and YP. So that means, and they're right, so that means that this is on the angle bisector. Okay, so because theirs are on the angle bisectors, we can set these equal to each other. So 4x minus 1 equals 2x plus 5. So that would be minus the 2x would be 2x minus 1 equals 5. So 2x equals 6 when we add 1 to both sides. X equals 3. Now I need MYW, so I'm going to plug it in here. So 2x plus 5, 2 times 3 plus 5. Sorry, I was getting in the middle. 6 plus 5 is 11. So the measure of this angle is 11. Now if I look at this one, it should have drawn the right angles. It does have LJ being equidistant from LF. So that would mean we have, if this angle is 58, this one over here, LYF, is also going to be 58. Okay. Now, similarly, we know this is 19 and this is 19, so that means this is an angle bisector. Because this is an angle bisector, I know that these two are equidistant from each other. So 2x plus 5 is equal to 7x. Okay, 7 5 would equal 5x. Oopsie. X equals 1. Now I'm looking for IU. So 7 times 1 is just 7. Okay. So again, when in doubt, what are you doing? Send them equal to each other. Now, again, looking at the point of concurrency, if you draw all three angle bisectors, they will meet at a point, and it is called the InCenter. Okay, this one is the InCenter. The circumcenter was the center of the circle that circumscribed, right? The perpendicular got you the circumcenter, which circumscribed the circle. Now we have the InCenter from the angle bisectors, and that is inscribing. So it is the largest circle that you can put on the inside of the triangle, right? That's going to be the largest one that you're going to get. It's going to touch each of these sides. It has a theorem as well. It is equidistant from the sides of a triangle. Where does that come from? Well, right, if you draw a triangle, no matter where I drew the radius, it's going to be equal. So that's why, right? If I could put this in a circle, it's going to be at the radius of the circle. So again, I cannot stress this enough. These are not necessarily on the angle bisectors. Okay, we're just saying if I draw a line or a segment from my InCenter to the side of my triangle, it's a perpendicular line, right? We always are drawing the perpendicular segments. It's going to be, they're going to be the same no matter which side you draw it to. Okay. So, similarly, we're going to ignore that because we don't have any information for it. So point A is the InCenter of triangle PQR. Okay, find the measure of each below. The reason I scribbled out AU is because they didn't actually give me a measurement. I could find the measure of AU if I knew that, number one, that this is perpendicular, and number two, if I knew that, either this side or this one, because these ones would be congruent from the InCenter theorem. But ultimately, what do we know? We are looking for ARU. ARU. Okay, so what do we know? This is an InCenter, so these are angle bisectors. So this is 40, this is 40. Okay. Angle QPK, QPK. Again, this is an InCenter, so these are angle bisectors, so I can set them equal to each other. So I'm going to add the 9 to both sides, 11. Subtract the 3x from both sides, x. Now I want to plug it into QPK, so 3 times 11 plus 2, 33, plus 2, which is 35. Okay, that's all there is to it. So I know there's a lot of information here, but ultimately what are we really doing? Well, we're using what we know about perpendicular bisectors and angle bisectors to solve for sides or angles. And ultimately, when in doubt, if you don't know what to do, if you set it equal to itself or set it equal to the other piece of information you have, that's a pretty good idea of what to do. All right. So let me know if you have any questions. We are going to practice this more tomorrow, but let me know if you have any questions, and have a great day.